So I want to bring to the stage now the next moderator for the panel about Mars sample return is Mary Engola. She is the communications person at Aerojet Rocketdyne, but she says, Janet, dispense with the long bio. She said, what I want to do is I want to tell one fun fact that might not be told in a person's LinkedIn bio. So here is Mary's fun fact. Between 5th and 6th grade, she was given an Army scholarship to attend U.S. Space and Rocket Center Space Camp, and that got her hooked. How many of you, just by either a show of hands or a hand clap, would say you also went to space camp? Anybody out there? Okay, a few. All right. So without further ado, let's hear from Mary about Mars sample returns.
Hi, I'm Mary Engola with Aerojet Rocketdyne, and I'm super excited to be moderating this panel about the Mars sample return. We just heard about the human landing system, so we learned about the humans, so we're going to switch gears a little bit and talk about the robotic precursor missions to enable those human landings. And so with me today, I've got Jeff Gramling from NASA, I've got Dave Murrow from Lockheed Martin, and I've got Albert Haldemann from ESA, all up on stage with me. So Mars Sample Return is a joint NASA and ESA mission that's going to robotically collect rocks, samples, and atmosphere and return them here to Earth for analysis. You know, we have collected samples from the moon, from asteroids, but this is the first time we've gone to Mars, or any other planet for that matter, to collect a sample. And so I think that's super exciting, and I can't wait to talk about that with all of you. So to my left, and joining me in person, which I'm thrilled to have somebody else in person with me, is Jeff Gramling. Jeff is the Mars Sample Return Program Director at NASA headquarters. One thing that you won't read in Jeff's bio is that he and his wife are on a quest to visit all of the national parks. So Jeff, you'll have to tell us which national parks have those Martian landscapes that we should all go visit. We also have two virtual guests, Albert Alderman from ESA and Dave Murrow. Albert is the Mars Chief Engineer for the Mars Exploration Group at ESA. Fun fact about Albert is that he flew Hawker Hunter jet aircraft for the Swiss Air Force in the 1980s and the early 90s. And one of the planes he actually flew was located in the Grand Canyon for a while, and it had nose art painted with his name on it. And then we've got Dave Murrow, and Dave has a real passion for Mars, and I think it probably rivals some of you in the audience. And so that passion began when he was in high school, and he received a copy of Scientific America with a picture of the Viking lander on the cover, and he says that was kind of the equivalent to his Apollo moment. So thank you, all three of you, for joining us today. So before we get into the Q&A session, we're going to let each of them tell you a little bit more about their role on the mission, and then we'll take some questions. So with that, Jeff, you want to kick us off?
Sure. I've got some slides, so we can go to the next one. I'm Jeff Gramling. I'm at NASA headquarters. I'm the program director, as Mary mentioned. So what are we trying to do here? I think most of you are aware we've been trying to do sample return for a while. We are now in phase A, and we're making progress, but what's it all about? It's been a priority of the decadal surveys, actually the past 3 decadal surveys, and the most recent one was just released a month or so ago. And of course, it'll be the first round-trip mission to the surface of Mars or to any other planet. Why are we interested in going to Mars? For a variety of reasons. We're going to talk a little bit more on following charts about what we believe we bring to the table to support the future human missions to Mars. But in the science domain, the oldest known life on Earth existed about 3.5 billion years ago. At that time, we believe the climate on Mars was similar, and that therefore life could have evolved on Mars. But for other reasons, in the absence of plate tectonics, much more of the ancient surface of Mars is available for us to sample than it is on Earth, and to bring back and study to help us understand, the keys to life in our solar system. So the first billion years in life's beginning in our solar system, the record is on Mars. So we think there's quite a bit of science and value, and that's kind of what's behind this mission. We can go to the next page, please. So everybody, I think, is aware that Perseverance has successfully landed. It's been collecting samples, and what we're doing is we're on a mission to collect scientifically selected samples. So that's what's driving where Perseverance is going to collect samples. It's also what drives the complexity of the mission in large measure. So to date, Perseverance has sealed 10 tubes. Of those, 8 are paired rock samples. Why are we collecting pairs? At some point, we will establish a cache on the surface of Mars where Perseverance will continue to retain samples, and in this way, we've got duplicates in a sense for us. So we want to have backups to the samples we're collecting. We're also currently in the middle of Perseverance of doing engineering studies in terms of selecting a near-term landing site, and we're putting together a science community workshop that will probably be in late September to get the science community to weigh in on the collection of samples that we're considering depositing, and really what we're looking to do is to make sure that it's considered by the science community to be a return-worthy collection. So we can go to the next chart. And this really just shows, as I mentioned, all driven by scientifically selected samples. Perseverance has taken quite a journey already. In the upper left, you kind of see 3 forks. That's an area we're considering for possibly establishing the first cache, and it's already been surveyed to a large extent with a combination of Perseverance itself, and then we've actually been using Ingenuity to help us survey potential landing sites. Next page, please. All right, what is a Mars sample return program? What is the Mars sample return campaign? Well, the campaign is an overarching, it began with Perseverance landing. Perseverance is, of course, collecting the samples that we're hoping to bring back. And then we've got the Mars sample return program, and that's the remaining flight elements. In other words, we're going to go to Mars, we're going to land on the surface, we're going to collect the samples that Perseverance has taken. We're going to launch off the surface of Mars, and we're going to bring those samples back to Earth. The Earth Return Orbiter that ESA is building has a capture, containment, and return payload that is being built by NASA at Goddard. That payload is what largely accomplishes our back planetary protection regime, and then it also contains the Earth entry vehicle that will ultimately, we're looking to land in the desert at Utah. And then on the back end, there's a sample receiving facility that is yet to be established. The Perseverance operations and the sample receiving facility are the responsibility of the Mars exploration program at headquarters under Lori Glaze, who will be here to talk to you tomorrow. So we can go to the next page. This chart really focuses on what value do we think we contribute to future human exploration. And there are a few questions. First and foremost is what is the dust look like? Is it toxic? What's the makeup? And what are the expectations, for instance, on seals or astronaut suits that we've got to worry about? So that's the first thing. Because the global dust storms are just that, global in nature, we feel like we can get a pretty good idea with a point or a few samples that will help give us invaluable information that will help feed or inform the future human missions. Other things is is what can we, with a better understanding of the regolith, can we potentially use it for radiation shielding or as building blocks potentially? And then the other thing that we hope to understand is are there toxins that we need to worry about? So all of those things are ways we think we can help inform future human missions and make sure that they can be conducted safely. Next page, please. And basically, Mars is the next most accessible destination for humans. We believe that once there's much we can do to help make sure that human missions can be conducted safely, and at the same time, once we do have humans on the surface of Mars, we think there's quite a bit of synergy in terms of how they can help us, further our science objectives on the surface of Mars. And next page, please. And I've got a couple of quick movies just to show you what we've been doing in Phase A. What you just saw is a prototype. What the cylinder you're seeing is a surrogate for the Mars ascent vehicle, and what you're seeing is it being kind of launched up into the atmosphere, so that when it fires its engines, we reduce the coupling with the sample retrieval lander. So making good progress there. And on the next page, we've already done some drop testing of the Earth entry vehicle out in the desert of Utah. And that's what you're about to see here. In the picture to the left, what you actually see is exactly where it landed. So we've got good preliminary results there that are helping us further our designs. And I think the next page may be the last one. So I mentioned that we're in Phase A. We believe now is the time to do Mars sample return. We've got Perseverance on the surface of Mars, and we've updated our reliability analysis, and we have confidence that it will be alive when we land on Mars and be able to be a pathway to bring samples to us. We've also got orbital relay assets in place, and over the last 3 years, together with our ESA partners, we've really scrubbed our architecture, and I think we're making good progress. We've got the team, and I think now is the time to make sample return happen. So thank you very much.
All right, so I'm very curious about the atmosphere collection. So what are you trying to collect in the atmosphere? Are you trying to learn about sort of the methane, the trace elements? What is it in the atmosphere you're looking for with the collection there?
So there was a strong desire in the community. I am not a scientist.
Okay.
There's a strong community to get an atmospheric sample. That hadn't been part of the original Perseverance design. It so happened that one of the first tubes we collected, is atmosphere. So we actually now have an atmospheric sample in one of the tubes. Maybe I whizzed past that on the chart too much, but of the 10, 8 are core samples. One was atmospheric and one was a blank. I think it was a broad question. The scientists were looking to get a sample back and bring it to Earth where we can use our advanced instruments and laboratories. And I forget the exact studies they were going to do. And it had to do with the composition and I don't remember.
Okay. Well, we'll ask Lori tomorrow when she's here.
She would.
She can tell us a little bit more about that. So since this is the Humans to Mars conference, we want to eventually get to Mars with humans. What are some of the biggest challenges with this mission?
Everything is challenging, right? So we're doing quite a bit of first. Obviously, whenever we go to Mars, we're challenged with mass, right? We're landed mass. That's the first big challenge. We're trying to. Obviously, we've got to take the Mars ascent vehicle. We've got to land. We've got to then launch. We've got to coordinate our OpsCon, right? We've got the surface OpsCon where we're still studying it. We may be looking to try to do this without MMRTGs, which means we have to operate between the dust storm seasons. So the whole coordination of the Perseverance, where we land. We're trying to use pinpoint landing to land as close as we can to minimize the distances that Perseverance or Fetch rover would have to drive to return samples. But it's all about margins, and it's a complex surface ops con. Not to mention coordinating all the relay assets so we can use all of the sols effectively. And then, of course, launching from another planet, we haven't done that before, right? It's a big challenge, and in a mass-constrained environment, to make that work is going to be tough. I think we've got a good group of people at Marshall who have been working this for a while. We've now got some contractors working this. So I think we've got the right people working that problem. And then, the Europeans are leading the Earth Return Orbiter and sample fetch rover and the sample transfer arm, actually, that is on the lander that will take the samples from Perseverance or the fetch rover and then place them in the orbiting sample container in the nose cone of the MAV. But as I mentioned, the Earth Return Orbiter is going there. It's going to provide a relay function for the assets on the surface when we're executing our OpsCon. And then, like I said, we're building the capture, containment, and return payload for that spacecraft at Goddard. And that's got to solve some unique back planetary protection requirements, which, we're kind of the pathfinder there too. So we're working all that out.
Before we get those humans, and so we'll have a lot of those same issues probably with humans. So we're happy you're working all that out for us ahead of time.
But we've got, I've been on this for about 2 years now, and we've got, a large part of the agency working this, our European colleagues. So I think we've got a great team, and I'm pretty confident we're going to be successful.
I'm excited for you. I'm very excited for you. So what do you think is the most beneficial aspect of this mission will be for those future human missions?
As I mentioned, I think it's having to actually, it's the ability, just as, to understand if there are any dangers there. And I was actually talking to one of the scientists this morning. She was explaining to me that even on the lunar missions, we learned things about the impact on the astronauts' suits that were unexpected. So I think us understanding toxicity and the characterization of the dust and just a better understanding of what can be used in situ, I think all of those things will help inform us and be able to make decisions about, the more we know, the less we have to worry about, right? So we can right-size things potentially and save mass in areas with, based on knowledge we may have.
Yeah, that's wonderful. My day job, I work a lot on this beautiful rocket behind here, the SLS vehicle. And so, know a lot about launching from Earth, but we're going to be launching from Mars. Can you talk a little bit about the differences of launching on Earth versus launching from Mars?
Well, the density of the atmosphere is one, right? Maybe one of the biggest ones. The other challenges, I don't know that it's strictly launch vehicle related, but you asked me about complexity before. The other thing that we've got to do is we've got to rendezvous the Earth Return Orbiter with the samples that the MAV is launching, and so that's another challenge. We don't kind of have the same, as much instrumentation as we would here on Earth. So the whole, I'm not a launch vehicle person, but I'd say the mass constraints, among other things, are kind of things that we're having to take into account when we're doing the design.
I think we had a question from the audience.
Tell us about the witness sample. Is that really a blank that you never opened and is just bringing back an empty tube that we send up?
That's a good question. I'm sure if Albert were here, he would know the answer to that better than I do.
Now, I understand something about the planetary protection idea, that we're supposed to protect us from anything from them. Dr. Robert Zubrin would say, don't worry about it. It's raining on us day and night. But for us to protect Mars from us, I have my doubts about that. And I think we should treat Martian microbes under the soil sort of like we disrespect our own microbes here. But a witness protection program, seriously?
All right. Do you want to talk all about planetary protection and sort of what you're doing for both, forward and
Sure.
backward contamination plans?
Obviously, planetary protection is something that we take very seriously. We're working, our practice at NASA is we're working with our planetary protection officer. Ultimately, we have to satisfy him and the community that we're doing this safely. I think we've got a model in what we did on Perseverance. And then obviously the new element here is the back planetary protection. And again, we've got to work with our planetary protection officer, follow our procedures at NASA to convince ourselves and the community that we're doing this safely. And so, our designs are reviewed by our standing review board per agency practice, but then we've got the whole planetary protection process. And of course, the NEPA process has just been kicked off, actually. So I'm confident that we've got the right processes in place and that the right questions will be asked and that we will do this safely.
1, 2, 3.
On the back planetary protection piece of it, it's a balance in a sense. We've got to balance sample integrity and back planetary protection. So in other words, things that we might want to do to increase our confidence in back planetary protection, heat specifically may not be what we want to do to the sample. So there are a lot of elements that we're trying to take into account and make sure we do the right things. But again, it won't just be us grading our own homework. We've got processes in place to make sure we do it right.
All right, looks like we've got Dave and Albert back, so super excited to have you. Albert, let's see if we can hear you. Right. So we're
Happy to be here.
We're excited to have you.
And Washington, D.C. from The Hague in the Netherlands.
We're thrilled to have you. So we've been taking some Q&A. We just were wrapping up a question about planetary protection, but we're anxious to hear your charts. So we're going to see if we can get those up and have you deliver them.
Thank you so much. So I'd like to give the ESA perspective on our partnership with NASA and how I see the link between Mars sample return and humans to Mars. Next slide, please. As Jeff mentioned, a fundamental contribution that ESA is making to the Mars sample return architecture is Earth Return Orbiter, or ERO. And it does what's advertised on the box. It's going to travel from Earth to Mars and back again. And I think in the context of humans to Mars, that in itself should be an exciting stepping stone accomplishment to look forward to. At Mars, of course, ERO has mission tasks that Jeff mentioned, and that has to make happen. It has to observe the launch of the Mars Ascent System. Prior to that, it provides relay communications for the surface assets to coordinate the collection of the samples. And then once the orbiting sample is in orbit, the Earth Return Orbiter has to find it and rendezvous and capture it. So next slide, please. I could have mentioned on the past slide that the Earth Return Orbiter is an absolute beast in the spacecraft. It'll be about 7 tons at launch. It's 38-meter wingspan. It's about 6.5 meters tall. So it's a big craft, and that has to fly from Earth to Mars. And the way we're going to do that is by using electric propulsion as a fundamental element. It's mission enabling. It's the use of electric propulsion that actually means that a 7-ton spacecraft to Mars can be launched by the Ariane 64, which is the yet-to-be tested, launched, but will be at the end of the decade the main launcher for the European Space Agency. Electric propulsion is 10 times more efficient than chemical propulsion, so it needs less propellant. We're using xenon for the EP. We did study an all-chemical propulsion mission And it would have been a 13-ton mission, and that would not be launchable, at least not by anything we have in our stable or in our plans. And if you had that heavy a spacecraft get into orbit at Mars, would also be difficult. Aerobraking with something that hefty would be a challenge, if possible at all. Another benefit of electric propulsion is we can demonstrate it on the ground. So there's some tech with the RIT-2X engineering model, part of the technology development activity that we did in the phases of Aero development. The primary challenge with this engine, which is not the one that would have heritage from the Bepi-Colombo spacecraft, is that it's a gridded ion engine, and we need to ensure that its lifetime meets the needs. So I can happily report that the engineering model number one successfully completed confidence test, and a full performance test is underway. The life test will start in June and will last for quite a while. We need to prove 20,000 hours. Next slide, please. So the other major technology challenge is the detection and tracking of the orbiting sample. It's a basketball-sized or soccer ball-sized or football-sized sphere, as you wish, and you need to detect it at a range of about 1,800 kilometers. So we have a narrow-angle camera to do that, and we also have a LiDAR for the close approach. The narrow-angle camera is used for the long-range detection and the tracking, and the detection is like, I think it's like spotting a 16-inch laptop screen that's in Seattle from somewhere around the location of JPL. It's a challenge. So the development has benefited from a thorough technology development activity as well during the study phases, and it's based on a flown detector that is part of a star tracker. That the NAC will track down the Oz until an approach distance of 500 meters, and from that point we'll be using the LiDAR. The LiDAR is one that has been used in space. It was the part of the rendezvous system of the automated transfer vehicle that ESA built for bringing supplies to the space station. Let's see. We also note that the whole image processing benefits from Airbus heritage. That's heritage that Airbus has on ATV, but also from their scientific and military space applications. Finally, the optical detection is indeed a key interface with the overall campaign. It requires working with the Oz design team and the Mars Ascent System design team to make sure that we can line all of those elements up for a successful detection and capture. I want to go a little bit quickly since we lost some time with the AV trouble. There are some other challenges, and the next couple slides will show some illustrations of a couple of ESA and cooperations that we've been working on as we have been working towards confirming the architecture for Mars Saturn. Next slide, please. So a key challenge is to fetch the samples quickly. This is a picture of the locomotion breadboard of Sample Fetch Rover being tested. It has 4 wheels. The wheels are provided by the Glenn Research Center. The 4-wheel system is faster than a 6-wheel system. And the reason we have to collect the samples quickly is that the Martian system has a limited lifetime to the surface, and we definitely want to launch the MAS before the global dust storm season. Next slide. ESA is contributing the sample transfer arm, STA, to the sample retrieval lander. And the sample transfer arm has to grip all of the sample tubes and then place them into the orbiting sample container. So sure, you can imagine, we need to ensure that that is a fully reliable system and that every sample is transferred by the STA is transferred perfectly. And we're working on that with, in cooperation with JPL teams. We're cooperating with our ESA team and our European industry team to make sure that we have a robust system that plugs into the SRL lander. I want to make some additional remarks. Next slide, please. At ESA, exploration is, Mars exploration is not a separate element. ESA is partnering with NASA on Mars sample return, but it's not just Mars that we do. We are housed within the Human and Robotic Exploration Directorate, and that directorate does all of the things illustrated on this chart. So I work in the same building as people at ESA who are working on ESA's contributions to Gateway, ESA's contribution to Artemis, as well as ESA's contributions to the space station. And so we are definitely tuned in to Mars sample return being part of a longer-term exploration program to bring humans beyond low Earth orbit on the way to Mars. So that is definitely part of our stated goals within our exploration program. Next slide, please. So the title of this slide is Terra Novae. That is the new and hopefully more exciting name of the more bureaucratic version title of the European Exploration Envelope Program, which of course has the acronym E3P. But Terra Novae is the moniker we give it to really capture the idea that we want to exciting exploration activities, and we expect the Earth Return Orbiter experience, that interplanetary return operations, combining multiple critical mission events, for example, will form a base in conjunction with his other human and robotic exploration programs, Artemis activities, contributions to Gateway, to some of the concepts and things we want to do contributing to humans to Mars down the road. So that is definitely part of our overall program. I'll sort of add that let's not forget in situ resource utilization, that the samples we bring back will be able to confirm the scope of the simulants that are typically used to validate in situ resource utilization technologies. So we need the samples back for those purposes too. Thank you.
Thank you, Albert. Really appreciate that. We're going to turn it over to you now to talk about Lockheed Martin's role in this mission and see if we can bring up your slides.
Awesome. Well, thank you very much, Mary, and thank you. It's a real honor to be sharing the stage with Jeff and Albert. So thank you. Even though I'm not actually sharing the stage, I got diverted in my flight yesterday, so I'm not in Punxsutawney as Jeff guessed. I'm actually in Pittsburgh, which is about as far from DC as the orbit at Mars is from the surface. So just to put it in perspective, I'll be there tomorrow after hopefully 7 minutes of terror. So I'll talk a little bit about Lockheed. Next chart, please. I'm going to take kind of a three-step process here. I'm going to talk a little about the past, a little about the present, and a little about the future. First, just to remind you, we've been doing this a long time. We being NASA and Lockheed and the international community together. Down there in the bottom right, you can see Viking that we all did back in the 70s. We did planetary protection that time by baking out the entire lander. We end up, nowadays with our landers, we end up cleaning them with alcohol and doing a bioassay. We'll take the planetary protection on the return just as seriously as Jeff mentioned. I know this is a Lockheed Martin brag chart, but we've been involved in every mission to Mars, and so it kind of points out the entire program. And so let me point out a couple of pieces. There, just to orient you, this we call our swoosh chart. It starts at the bottom right and swooshes over to the left and around up to the top right. There along the bottom, you can see Mars Odyssey in 2001. You can see Mars Reconnaissance Orbiter in 2005. Both of those are still there, providing both science and relay assets. Going a little further around the swoosh, you can see Maven and Insight, which are also at Mars. And then our whole series of aeroshells. We've been doing aeroshells for a long time, and 2.4 meters was the smallest one we did. 2.65 is kind of a standard size for Mars Pathfinder. This one, can't believe I'm using meters and Albert used feet, but this one is 4.65 meters for Mars sample return. So if you go all the way to the right there, you'll see the Mars sample return. You can kind of see the Lockheed Martin scope there, which is really the MAV, pieces of the lander and the Earth entry system. So if we go to the next chart, I'll dive into a little bit more detail. You've seen our past. Now this is what we're working on right now from our sample return. And again, just a little guided tour over there at the top left. That's what the vehicle looks like on its way to Mars. That's the cruise stage with a fairly large solar panels there attached on the cruise stage to the full-up aeroshell, all buttoned up. And one of the reasons why that solar array is so large is that we actually go on this long Type 4 trajectory in order to land at the proper time to avoid the dust storm seasons that Jeff was mentioning. So on the right-hand side there, the little stack going through the pieces, the cruise stage is at the top. And so it's got a propulsion system. It's got the arrays I mentioned. You're looking at some thermal radiators there. It's got a bunch of sensors and telecommunications equipment that help guide the spacecraft all the way to Mars. And the little green star there really is just the sense that it's a Lockheed Martin scope. Again, I'm a company guy, so I guess I have to brag a little bit. But I'm more a Mars guy, really, honestly, so it's really great to be here. Then there's the back shell and the heat shield, which, of course, those two pieces come together as kind of a clamshell to hold in and protect the lander itself, called the Mars Lander Vehicle, or MLV, in the middle there. So it's all buttoned up to go in for that 7 minutes of terror I was mentioning earlier. And as we come in, we move some ballast masses around to be able to change the CG of the vehicle and be able to guide the entry. For this particular entry, it's a landed leg vehicle, much more like Insight, Viking, and Phoenix than the Sky Crane Perseverance lander. And so the legs will deploy after the spacecraft is lowered out of the back shell, and the spacecraft will do a very large divert maneuver to divert to exactly the right spot on the surface so that it's as close as it can possibly be to the cache samples that, again, that Jeff mentioned. We want to basically find that precision point so the fetch rover that Albert is going to supply has as short a distance as possible to drive around, go grab the samples, and bring them back to the lander. So then, continuing our guided tour over to the left, you'll see the Mars Ascent vehicle. That's the latest kind of public image of it. You can see that it's a two-stage vehicle. The diameter section there at the bottom is the first stage. It's a solid rocket motor provided by our friends at Northrop with a thrust vector controlled engine at the bottom. And then the upper white portion is the second stage. In some ways, it's not that much different from a rocket here on the Earth. It launches, it uses one stage to go most of the way up to orbital velocity, The second stage spins up. In this case, it's a spinning upper stage, and it's through that method guided. It burns and puts the spacecraft in orbit, and then the orbiting sample is released as once it's in orbit, and it's in a known position, known orbit. So that's about how the ERO can find it. So in some ways, it's not that different than an Earth launch vehicle, but there are some key differences. And the first one is the one you saw from Jeff's chart earlier, where instead of being erected on a stand and launched from a vertical position where it pushes very hard against the launch infrastructure, if you will, this one is lofted up into the air by a spring-loaded system and then launched as it goes up into the air. So in some ways, it's more like a missile system than a rocket system. And, you know, we're building this in Huntsville, Alabama with our Marshall partners and also folks that do some pretty important missiles for the U.S. military. And they're bringing a lot of that capability and expertise to bear for NASA. We're really proud of the fact that we can bring capabilities from across our portfolio to help NASA and to help the exploration of Mars. So that the other challenge I'll say is really the packaging. That whole thing, the diameter of it is only a couple of feet across, and it's about 3 meters in length. So the packaging is much more tight than it is in most spacecraft. So that's an issue that we have to solve. And again, our missile brethren down there in Huntsville are very skilled with that, and so we're very confident in their abilities. So that's about all on this chart. I'll just go to the next one and remind you that in addition to thinking about the past 50 years of going to Mars and now being in a position to bring back samples, we're also looking to the future. And I think you saw this chart earlier when Christy Edwards was up on stage. This is our Mars base camp. We see in the long run the human program taking humans to Mars. This is one concept with 2 Orions and a launch vehicle that you can see there in the top right, where it goes down supersonic retro propulsion down to the surface. The astronauts get out, look around, do some science, and come back and bring samples back to the base camp. So we're pretty excited about this concept as sort of a way to pull us all into the future. Just like ESA at Lockheed Martin, our human spaceflight and our robotic exploration are all part of one organization. We call it Commercial Civil Space. And so we're always thinking about how robotics and human spaceflight go together, and Humans to Mars is just one more example. So we really are excited about being sort of the robotic precursors, and also, excuse me, also designing for the long-term future. So thank you for your time and attention. I see that I'm only 1 minute over, and maybe there's still some time for questions. Thanks a million, and we'll see you tomorrow.
Thanks, Dave. Appreciate that.
So I was curious, you still feel that a sample return is going to give you more bang for your buck than just trying to do in situ studies, soil studies, and stuff like that?
We really plan that it will. There are things like doing really detailed crystallography, looking for trace minerals that are at level that tell you a lot about the formation conditions of the rocks, things like that. Well, we would need to be able to land tons and tons of robotic equipment on Mars, which we have on Earth. So we bring the samples back there. We have the equipment available, and of course, it will improve here on Earth in time too. I think having we have samples from Mars in the sense that we have meteorites, Mars meteorites on Earth. The thing that is new about acquiring the samples with Perseverance is that they are acquired. We know where they come from, and we know the geological context that the samples are acquired from, and therefore the specificity of the information about Martian history is much better. And in fact, the Perseverance landing site was chosen and in Jezero Crater with a delta in a location where habitability was expected, so that the expectation of seeing information about environments that we do address our most fundamental scientific questions of Mars. And there are instruments on Perseverance that are doing great science, but we would be able to do orders of magnitude better with tools that are on in Earth labs.
Dave, do you have anything you wanted to add to that?
Yeah, sure. I would just say I agree completely with Albert. And, you know, we work very, very hard in the science domain to miniaturize our instruments, and we tend to have very focused experiments where we take something that is, you know, an age dating experiment, for instance, and we can do one thing with it. With instruments here on Earth, they're instruments that are as big as the labs at the hospital in your hometown or the most important research facilities in the world. We can just do so much more with, like Albert mentioned, with crystallography, traces of minerals, astrobiology experiments. And let me just call out the Apollo sample experiment that's going on. In 50 years, we've made a lot of a lot of progress here on Earth in instrumentation. And so we're taking advantage of that fact because the Apollo samples have been waiting for it. We might be able to do the same thing with the Mars samples. Who knows what we can look for in 50 years.
All right. Do we have another question? So Albert, during the break, we were asked about a witness sample and if that really is just going to go up and back. And so do you have anything you can tell us about the witness sample?
I'm not an expert on the samples on Perseverance. There's one, and they are meant to provide calibration information based on the environment encountered by the spacecraft and by the sample acquisition system during the process. I believe that there are open publications that explain the witness samples that are on Perseverance. They're in part of the Perseverance description. But I did hear that from the back room. We could hear what was going on in the questions. And yeah, I appreciated the quip about the witness protection program. That was a good one.
All right, well, thank you guys so much for participating. Very excited for this mission and can't wait to see the rocks and soil and most importantly, the atmosphere that you're gonna be returning. So I'm excited about that. Thank you, and I think I'm standing on the way to the break.
Thanks, everyone.